Hello and welcome to our ELECOMP Capstone Spring 2024 Summit virtual presentation. We're a team Aerocyonics and our project is Saint Dashboard Security Articles of Interest for Awareness, Outreach, and Actionable Intelligence. First, let's meet our technical directors. We have Daniel DeMays, President and CEO of Aerocyonics, Ram Pav, Chief Engineer at Aerocyonics, as well as Isabella Johnson, Software Engineer at Aerocyonics, as well as a URI 2023 ELECOMP graduate. Now let's meet our capstone designers. We have myself, Kyle Nadeau, a computer engineer, as well as Mara Corrado, another computer engineer. Aerocyonics is a company based in East Greenwich, Rhode Island, who provide expertise in hardware and software assurance. One item that the company produces on a weekly basis is known as the Articles of Interest. The Articles of Interest is a 200 to 300 page long PDF document which consists of 1,000 plus relevant cybersecurity articles on a weekly basis. The goal of Saint Dashboard is to improve upon this already existing service provided by Aerocyonics and offer a web-accessible dashboard which can be updated with relevant cybersecurity information weekly. For the overall project anticipated best outcome, there needs to be a user-friendly interface which users can easily navigate to find cybersecurity articles. We also need to automatically aggregate current security items, implement threat categorization so users can find specific articles with a given threat, implement actionable intelligence, and then useful metrics for the database. For our project, we specifically focused on implementing actionable intelligence into the Saint Dashboard program, in which our ABO for this specific part was achieved. For our capstone's anticipated best outcome, we need to utilize machine learning methods in order to identify mitigation articles, or in other words, an article which contained any information on how to mitigate a cybersecurity threat. We also need to identify specific mitigations and assign them to these verified articles. These programs that we developed needed to be able to interact with already developed software, which was developed before we started working on the project. The diagram you can see on this slide displays different avenues that you can take when making a machine learning program. For us on this project specifically, we focus on supervised learning for text classification. The economic impact for achieving a final product of the Saint Dashboard will save Aerocyonics time and resources weekly, avoiding them to have to produce the articles of interest. It will also offer them an ever-evolving web-accessible dashboard with relevant cybersecurity information, which is also easily accessible for users rather than the current PDF format. We have 4 overarching accomplishments for this project. One being the compilation of a list of articles to use to our trained model, the implementation of the model itself, generating data which we can use to train that model, and also assigning specific mitigations to articles. This is our overarching project block diagram, which consists of 3 main blocks and 2 outputs. For our first overarching accomplishment, that encompasses our first block, web scraping, or getting our initial links for machine learning. Then we have our 2 next accomplishments, which encompasses machine learning. This is where we can actually pull specific mitigation articles from our initial list. Once we have this list, we can then move on to our last accomplishment, which we can then classify and then store these articles into Saint's database. For our web scraper, consisting of our first block, we need to find links leveraging Google and other search engines. This would pull general cybersecurity articles posted within the past week. We would then use this as the input to our machine learning program. For machine learning, the team developed a working prototype which would be trained on a set of test data found from Kaggle. This was done so the team could effectively make a model that would be able to learn from a set of data. After making this model and understanding that the metric output was viable, we moved on to generating a data set that would be useful for this project specifically in identifying mitigation links. To develop our machine learning model, we followed the simple functional block diagram seen here. We first need to process data by tokenizing it and transforming the text data into tensors or matricium numbers. We then went through the training loop, updating parameter values based on our optimizer as long as the loop was still continuing. Once the loop was over, we would output the metric values in the results of the trained model. In order to generate the dataset, we followed this functional block diagram seen here. Our first step was utilizing an API, which would then help us find mitigation articles based on our certain keywords. We would then extract the body text of each article and then split them into phrases. After we acquired these phrases, we could then use a method to determine if it was a usable phrase for a machine learning dataset and then add it to the dataset if so. A method was also made to normalize this dataset, which would then remove any cases that would hurt the machine learning process. Here are some of our trained results from the model, one result being from January 30th and one from being from April 15th. What you're seeing here are two confusion matrices, and how you read these is in the top left is a true negative, and in the bottom right is a true positive. As you can see, the January 30th model did not perform as intended. This was due to a lack of data in our dataset. Throughout the semester, we have worked on improving this dataset significantly, and the new confusion matrix that you can see in April 15th is much improved, only seeing one false negative and three false positives. As of today, our model's metric accuracy is 93%, which is a significant improvement over the previous training, which was 73% training accuracy.
And now I will go more in depth on what we do with these verified mitigation links. And what that process is we classify these mitigation links and then we store these links and their information away for further use. So first and foremost, we assign threats to the mitigation links. This is done using an existing Saint method that uses the contents of each article to assign their threats. After that is complete, we use the threats that are assigned in the previous step to assign mitigations using a mapping script that I will talk about more in depth in the next slide. And finally, after that whole process is complete and we have our threats and mitigations, we then store the mitigation links and their classifications into a database that is handled by Aerocyonics. As for the mapping script I mentioned prior, if you could see here on the right, if you could imagine that the X column are mitigations and the Y column are threats. And as you can see, this red triangle and the red square both point to the same red circle. If you could imagine this triangle is a mitigation and this square is another mitigation, they point to the same threat. This just goes to show that one threat could have multiple mitigations. So this mapping script allows us to assign multiple mitigations to one threat. And there's even cases where multiple threats are assigned to a single article. So we would also have to assign threats to mitigations to all those different threats that are in one article. The content is stored in a key value format where the key is the threats and the value are the mitigations. And to go more in depth on storing everything, the data is converted into an organized format. This structured data is uploaded to the Aerocyonics database, and this allows for the data to be secure and easily retrievable so the Aerocyonics team and teams down the line can access this data whenever they please. All in all, this whole project consisted of Kyle and I scraping the web to extract URLs that were cybersecurity articles. We then used machine learning to process this data and to train the machine learning model. After the machine learning model was trained, we were able to use this model to identify which article URLs were mitigation links. And finally, we classified the data and we put it all away in a safe environment for further use in the future. As for the future of Saint, me and Kyle believe the most important thing is to increase the BERT model accuracy beyond 93% to get it closer to the 99%, just so that the more information is shown to the model, the less likely it is to be inaccurate. We'd also like to introduce incremental learning and hyperparameter tuning. Incremental learning is the process in which new data is introduced to a machine learning model that doesn't require for training to be started from the very beginning. So one can introduce new data and it can retain the things it learned from the previous data set without having to start the process all over again. Hyperparameter tuning is just introducing more varied data. This allows for the model to have a wider range of different contexts so that it could be more accurate in determining what makes an article a mitigation article. We also believe that shifting the threat mitigation mapping to a more ML-based process would be very suitable for this project because as cybersecurity is ever evolving, if new keywords, new mitigations, new threats come about, one has to manually go in and change the mapping, add new words, get rid of some words. If it's machine learning based, the machine learning model will be able to pick up on the changes quicker and evolve with cybersecurity so that there's less manual labor needed to do this. And we'd like to thank all the people who helped us here for everything they've done throughout the year. Thank you.